Welcome to the Explainer. Today, we're diving into a really cool piece of code that solves a tricky puzzle. The question is pretty simple. Can you build a pyramid of blocks when all you know is the base and a few basic rules? Okay, so here's our game plan. First, we'll get into the puzzle itself. Then, we'll see how the code builds the pyramid, one layer at a time. After that, we're going to look at the search strategy, decode the main function that makes it all tick, and wrap things up with a really clever trick that makes the whole thing way faster. All right, first things first, we've got to get a handle on the actual problem we're trying to solve. It's all about understanding the puzzle and its very, very specific rules. So here's the core challenge, right? You're given the bottom row of blocks and a rulebook. Can you figure out if a full pyramid can even be built from that? And that's the key thing here. It's not about finding the way to build it. It's just about knowing if any valid way exists at all. Okay, so the whole puzzle, and I mean the entire thing, hinges on this one simple idea, the trio rule. Basically, the code has a list of allowed trios. This list just tells us, hey, for any two blocks next to each other, like an A and a B, here's the block C that's allowed to sit right on top of them. That's it. That's the core mechanic. So what's the goal then? The whole point is to figure out if there is any valid sequence of choices that can take us from that wide bottom row all the way up to a single block at the very top. If we can find just one path that works, boom, the answer is true. Okay, that's the what. Now for the how. How does the code actually go about building this thing? Let's dig into how it figures out what the next level up could even possibly look like. The process is actually pretty methodical, pretty smart. Think of it like the code is sliding a little two-block window across the bottom row. It starts with the first pair, say AB, and looks up all the possible blocks that can go on top. Then, it just slides that window over to the next pair, BC, and does the exact same thing, and then CD, and so on. Once it's done that for the whole row, it combines all those possibilities to figure out every single potential next level. And that, right there, is exactly what the build next level helper function is for. I mean, its entire job is just to do that process we just talked about, to find every single valid next level that you could possibly build on top of the one you're on. Okay, but wait a second. This brings up a really important question. If one level can have, multiple possible next levels, how in the world does the computer decide which path to follow? This is where the strategy really comes into play. So you've basically got two choices here. You could go wide, which is like, okay, let's figure out all the possible second levels first. Then from those, let's figure out all the possible third levels. It's very systematic. Or you can go deep, and that's totally different. That's about picking just one possible next level and just following that path all the way up, seeing where it takes you. So which one does our code choose? It goes deep. It uses this really powerful strategy called depth-first search, or DFS for short. Honestly, the best way to think about it is like you're in a maze. You pick a path, and you just keep going. If you hit a dead end, what do? You turn around, you go back to your last intersection, and you try a different path. That's exactly what DFS does. Okay, so with that go deep strategy in mind, let's pop the hood and look at the engine of this whole solution, the DFS function. This is the piece of code that actually does the depth-first search. Check this out. This one simple line of code, this is the finish line. It's just asking, hey, is our current row down to just one single block? If the answer is yes, that means we made it. We built the pyramid all the way to the top, and the function can just yell true, and we're done. And right here, this is the magic of recursion. This is where the function calls itself. It figures out all the possible next levels. And then for every single one of them, it says, okay, DFS function, call yourself again, but this time try to solve the puzzle starting from this new level. It really is like those Russian nesting dolls. Each doll inside is just a smaller version of the same puzzle. And if any one of those little inner calls finds a solution and returns true, that true just gets passed all the way back up the line. Now, hold on. This deep search thing can get really, really slow if we're not careful. I mean, the number of possible paths can just explode exponentially. And what happens if we keep trying different paths that all end up at the exact same intermediate level? A level we already know is a dead end? That's a huge waste of time. To fix this, the code uses a technique called memoization. And yeah, it's a fancy word, but all it really means is remembering stuff you've already figured out so you don't have to do it again. I mean, think about it. If we've already proven that a specific row, say BCA, is a total dead end and can't possibly lead to a finished pyramid, why would we ever waste our time checking it again? It's a huge performance killer. Thankfully, our solution has a really clever trick to make sure that never happens. So here's part one of the trick, the memory check. Before it does any work on a new level, the very first thing it does is check a list or a set called visited. It asks, have I seen this exact row before? If the answer is yes, it knows instantly that it's a dead end. It doesn't have to explore anything. It just stops right there and returns false. And that brings us to part two. How does that visited set get filled up? Well, if the search tries a particular row, explores all the possible paths leading from it, and every single one of them fails, then right before it gives up and returns false, it adds that row to the visited set. It's literally learning from its mistakes. It's making a note. Hey, don't ever waste time on this path again. So when you put it all together, this whole elegant solution really just boils down to three key parts working together perfectly. You've got the rulebook, which is a map for super fast lookups. You've got the DFS engine, that recursive function that explores deep into the possibilities. And you have the memoization cache, a set that acts like a memory to make sure we don't repeat our mistakes. It's a beautiful system. And this powerful pattern, this DFS plus memorization combo, it isn't just for building pyramids. Not by a long shot. This is a fundamental problem-solving technique in computer science. You see it everywhere, from solving Sudoku puzzles to finding the best route on a map. Which kind of leaves us with one final thought, right? What other kinds of branching problems, like mazes or other puzzles, could you solve with this exact same pattern?